To begin, we must really just focus on some basic terms. Your textbook defines terms on the next few slides as they are written. The basis of problem solving is the scientific method. To begin, you must define your problem. Then you must observe and research to determine some explanation for this problem. That is the definition of the term hypothesis. Once your hypothesis is set, you perform experiments, and once the experiments are concluded, a theory may be obtained. The textbook definition of matter is listed here, but you can really define it as anything with mass and volume. Mass is defined as the quantity of matter in a material. Most of us use mass and weight interchangeably, but the fact is, mass is a direct measurement of matter, which is reported in grams or some grams-based unit, while weight has to do with mass and the force of gravity. The law of conservation of mass came about from the studies of Antoine Lavoisier. He studied the combustion of mercury and was the first to use a scale to measure mass before and after a reaction. The law is a very simple statement, and an example follows. Physical properties are those that are used to define matter. Things like density, melting point, boiling point, etc. Chemical properties, however, define the changes in matter. They indicate whether something will react or whether it won't, if it will burn, if it will rust, etc. All matter is classified as either a mixture or a pure substance. The definitions for the terms on this chart will be found in the following slides. An element is the simplest pure substance. The periodic table lists all of them with their symbols and names. Additionally, there are two categories of special elements. One of them is termed diatomic elements, and those are the elements that cannot be alone. Their names are bromine, iodine, chlorine, hydrogen, oxygen, fluorine, and nitrogen. A second category of elements is the term allotrope. An allotrope is an element that has different forms, like coal and diamond. The difference between a compound and a mixture is that in a mixture, the parts that are mixed together retain their own properties. The mixture is separated by any sort of means, such as evaporation, centrifuge, etc., but no chemical change occurs. Much of science deals with measurement, and when you consider measurements, you must consider both the precision and accuracy of the measurements. The definition of precision is the closeness of the set of values to each other. It's a measure of exactness, while accuracy is a determination of the correctness of a value. Notice on this slide, diagram A represents a person who has thrown the same way every time. All of the darts are in the same location, but are off-centered. That means diagram A represents good precision, but poor accuracy. Diagram B actually represents good accuracy, but poor precision. None of the darts are close together, but the average of the values is the center, which is accurate. Finally, C is the best of both worlds. It represents both accuracy and precision. In science, if we can't have C, we will choose A. It is far better to be precise than to be accurate without precision. In the case of A student or a teacher could analyze the process and determine what error had occurred. In diagram B, that really would be much more difficult. These are the standard base units used in chemistry. You need to know them and how to convert between versions of each unit. This chart represents what you will need to know about metric prefixes. Notice the symbol on the right is representative of the prefix itself. It will be paired with a base unit like the meter or second. The multiple indicates the number of the base units in one of the symbol units. For example, 1 megameter equals 10 to the 6th meters, and 1 centimeter equals 10 to the negative 2 meters. Significant figures are a method of rounding used in science to compensate for less than precise measurements. Note, this ruler is marked off in centimeters, so the measurement must be marked in one place past the centimeter or the tenth. The rule is simple. Whatever marking is on your instrument, you measure 1 decimal place past it. In determining what digits in a measurement are significant, you simply look at them. All non-zeros are significant. If there are zeros, there are one of 3 categories. The first are called captive zeros, or zeros between non-zeros. They are always significant. The next are leading zeros, which are zeros that precede a number, and they are never significant. And finally, zeros that are trailing or following numbers are significant only if there is a decimal point in the measurement. When manipulating measurements, you must account for the difference in precision. When multiplying and dividing, your answer has the same number of significant figures as the measurement with the fewest. When adding or subtracting, your answer should have the same number of decimal places as the measurement with the fewest. Exact numbers are simply conversion factors, and they are never considered when determining the number of significant figures to round to. In performing this calculation, you must assess how many significant digits are in each part of it. In the number 6.8914, there are 5 digits. In 1.289, there are 4 significant digits, and in 7.28, there are 3 significant digits. This means you must round your answer to 3 significant digits. So 0.734383925 is rounded to 0.734. When subtracting, you simply look at the points past the decimal, perform the operation, and then round based upon that. For example, 0.453 has 3 decimal places, and 1.59 has only 2. So I round this answer, negative 1.1370000, to negative 1.14, so that it has 2 decimal places, like 1.59. Scientific notation is a means of expressing very large or very small numbers in terms of an integer and an exponent. The value of a must be greater than or equal to 1 but less than 10. A nice thing about scientific notation is that the digits in a are representative of the significant digits in the measurement. When putting these numbers in scientific notation, you must make sure the value of the number is between 1 and 10. In moving the decimal, you must account for the direction you move it. When your initial number is less than 1, your exponent is negative. And when the initial number is greater than 1, the exponent is positive. So 0.000653 would be 6.53 times 10 to the negative 4. And 350,000 would be 3.5 times 10 to the 5th, etc. Temperature is a measure of hotness, or energy. Heat flows from an area of high to low temperature. The units of temperature you're familiar with should be Celsius, Fahrenheit, and Kelvin. Though Fahrenheit is the most familiar of the three, it is the least useful in chemistry. We focus primarily on Celsius and Kelvin. It is not necessary that you know the conversions between Celsius and Fahrenheit, but you do need to know the conversion between Celsius and Kelvin. To convert those two, you simply add 273 to your Celsius temperature value to get your Kelvin temperature. Density is defined as mass per unit volume. Common units of density are grams per cubic centimeter or cubic distance if for a solid, grams per milliliter for a liquid, and grams per liter for a gas. In analyzing a problem, you first need to decide what it is you're solving for. The question asks, what is the density of oil of wintergreen? In dealing with density, I have to know mass and I have to know volume, so I'll look for those numbers in the problem. Then I substitute them into my formula and I divide, making sure that you round your answer based upon the significant figure rules we talked about. The next couple of slides deal with practice conversions. This question asks you to convert milligrams into grams and then milligrams into kilograms. This is based upon the chart we talked about a few minutes ago. To begin, you start by writing down the number and the unit, 573 milligrams. I'm going to multiply that by a factor so that the unit cancels, which means I put milligrams on the bottom of this factor and grams on the top. I put a 1 with my prefix unit and the exponent conversion factor from the chart with the other and evaluate. In the second example, you have to combine units. If there are 10 to the third milligrams in a gram and 10 to the third grams in a kilogram, then that means there must be 10 to the sixth milligrams in a kilogram. In order to solve this problem, you have to know that 1 milliliter equals 1 cubic centimeter. Once you know that, it's much simpler to convert. So I start with 54.3 cubic centimeters, and I convert, so I put centimeter on the bottom and meter on the top. I define my relationship as dictated by my chart, and then I exponentiate that factor. In doing this, it allows my cubic centimeter to cancel out. and I end up with 54.3 times 10 to the negative 6 meters cubed over centimeters cubed. When I combine this and put it in proper scientific notation, I have to move my decimal point between the 4 and the 5. Because I've decreased this quantity, I must increase the quantity of the exponent by that same factor.